So we are going to talk about three special functions. The first one is known as a piecewise function. The second one is known as a step function. And the last one will be an absolute value function. That's the easiest, and I'm saving it for last. Okay? So we got to start with the piecewise function. And it's called a piecewise function because it is literally broken up into pieces. When you look at the graph, because we're going to be looking at the graph and you're going to be making a graph of piecewise functions, it's going to look like a bunch of disconnected graphs and disconnected lines because each line has its own equation. Okay? And the bulk of what we cover today will be piecewise functions because it's complex. Okay? You have to analyze and treat each piece differently and separately, even though it's all considered one function. And when we look at an example, you'll see what I mean. So let's take an example. And this is what the types of problems will look like on one respect, where we actually are given the piecewise function that we have to graph. Later on, we're going to look at an example of the graph that we have to write the piecewise function for. Okay? So one of the things I want you to keep in mind is that this f of x just means y. It doesn't mean f times x or anything like that. It just means y for all intents and purposes. It's a function notation. And so when we think about a piecewise function, we're really thinking about y equals x minus 2, y equals x plus 3. And so in this case, because there are two equations connected together by one brace, this forms one function made up of two pieces. Okay, the first piece has the rule y equals x minus 2. The second piece has the rule y equals x plus 3. These conditions over here actually tell us boundaries. So when we're going to put these on a graph, we're going to get boundaries for this specific function. Now the boundaries will change from problem to problem. It just so happens that this boundary for the first rule is x less than negative 1, and the boundary for the second rule is x greater than negative 1. So what that means is all the values less than negative 1 will get plugged in for x for this rule. All the values equal to negative 1 and bigger will get plugged in this rule. And so those x values get treated a little differently depending on which boundary we're talking about. Okay? So here's the way you want to think. Okay? You want to think y equals x minus 2 when x is less than negative 1. So it's conditional. These are the conditions. Bless you. When x is less than negative 1, you use this rule. Also, when x is greater than or equal to negative 1, you use a different rule. And you're going to look at some piecewise functions that will have more than two rules. We'll have 3 rules sometimes, 4 rules sometimes more. Not for this course, but most of the time it'll be 2 or 3 rules. And you just have to know when to apply which rule to what numbers. See, here's the great thing. You know how to graph this line y equals x minus 2. You know how to graph the line y equals x plus 3. In reality, that's all we're doing. We're just going to create a boundary for that line to separate the rules into two different pieces. So put that grid in your notes or turn your graph paper on because we're going to start graphing these things. Now, here's what's important to see. I put a dashed line right there on the line x equals 1. Anytime I have a vertical line, it's x equals something. Okay? There's no y for vertical lines. Because every x coordinate on this line is negative 1. And for this problem, that's the boundary. Okay? These conditions split this function into two parts. The less than negative 1 part, which is over here, and the greater than or equal to negative 1 part, which is over here. So which is why you're going to see this Okay? So I use the top rule on the left side of the x equals negative 1 because it's less than negative 1. And all these values for x are less than negative 1. So that's why I use this rule over here. On this side, all these values are greater than negative 1. So I use this rule on this side of the line, x equals 1. So instead of drawing one line, we're going to have two lines, but we're going to have parts of two lines, and one on the left side of that dashed line and one on the right side of that dashed line. Questions? Okay, so Cassie's question was, are those numbers always going to be the same? And the answer is no. Most of the time they're actually not. Okay? There'll actually be some space in between them, and we'll when we have to identify the domain and range, that's when that comes into play. Other question? No? Okay. All right, so let's get to it, the actual graphing part. Okay? So for the first equation, okay, I've done a little bit of work for us already. Right? It's in slope-intercept form. I know that the y-intercept is negative 2. I know that the slope is 1. But I made it 1 over 1 because to graph, when I plot the y-intercept, from there I just go up 1, right 1, and I have another point. So anytime you have the slope, of course I want to write it as a fraction because I need a vertical change and a horizontal change in order to find another point. Here's the thing though. If I follow this and I go up 1, right 1, and I have another point here, am I going the right direction? Where is the graph of x minus 2 supposed to be? To the left. So I'm moving right, and my line's going to go this way. Now, you can draw the whole line. If you want to draw the entire line just from there, and I'll do it. Let's just do it because I think some of you will like this. I draw the line, and I draw the whole huge giant line. The fact is, all of this over here is not part of the graph. Okay? It's all to the left of the boundary. So with Notability, you can do that. Okay? And then maybe with a different color, you go, all right, actually it's over here. That's where my line is. And then I just go in and I'm like, actually, let's just delete that line, and the line that I drew is deleted too, but kind of looks like that. Except the problem is it's still on the wrong side of the line. Okay, I really need to erase that much of the line. So now the boundary itself forces you to cut that line off. Okay? There's one issue though, and this has to do with this less than negative 1. This point actually doesn't lie on this dashed line, right? What do I put here? Because of this. Because I can't put a point there. What do you put when it's not or equal to? Open circle, right. So I really should have an open circle there. Now, this is one way to do it. You don't have to do it this way, okay? If you want to draw the whole line and chop it off, you're welcome to do that. If that makes sense to you, you can do that. Here's another way to do it, okay? Instead of moving to the right like we did with the slope, I can actually change the slope and make it work for me, okay? I can go down 1 from here and left 1. And see, notice I put an open circle there because on this line, x equals negative 1, it doesn't actually count. And I just kind of keep going. The trick is the line, the ray, will actually start from the boundary and work our way the other direction. So it ends up looking like that. So you have two options. You can draw the whole line and chop it off. If you want to do that, feel free. If you want to get a better idea of knowing how it starts at the boundary and going that direction, you can do that too. I'm giving you options there. So right, eventually you want to get rid of the y-intercept. But I have to have the y-intercept in order to graph the line, right? I have to have it at some point. But it's not actually part of the graph because it's to the right of the boundary for that rule, which is the point I think you're trying to make. Yeah?
Is the boundary from before when x is greater than or equal to negative 1?
So the boundary x less than -1. That's the boundary for that rule. We're going to use the same. It turns out to be the same boundary, the -1, and we're going to use it for this rule to draw on this side of the line. Okay. Questions so far? Any other questions? Okay. So now I have to do the same thing with this rule on this side of the line x equals -1. Okay? So I go and I look at the line y equals x plus 3. So now where is the y-intercept? 3. So I still have to graph that. Okay, the slope is still 1. So go ahead and graph that. So when I put the y-intercept, I put it at 3. And now I can go up 1/1 and draw my line. Now, what's interesting is that the line doesn't start at the y-axis. The line starts over here. Now, fortunately, we can tell where it goes. It's going to actually have to start at that point right there, -1, 2. Is that going to be a filled-in dot or an open circle? Filled in because of the or equals. So that's how the rest of it looks. Okay, and so I have to back it up a little bit to make it fit on the line, to make it go to the boundary. Question? Because of the or equals to. Because -1 for x is part of this rule. Okay, it's not for this one. Okay? Yes?
So how does this feel properly?
Yes. It'll always run right up to the boundary. It'll always run right up to the boundary. If it's an or equals to, it will lie on the boundary. So this one actually lies on the boundary. This one runs right up to it and is sort of next to it, but not officially on it. Okay? Now, this is the graph. You know how to graph straight lines. It's just, in this case, they're chopped off. They don't go on in both directions. And we're going to look at an example where it's chopped off on both sides. These are just rays. We're going to actually see a line segment here in a second. Now, we have to find the domain and range. Okay? So in order to do that, first we just start writing our D and our R. And one of the questions that you have to ask with the domain is which one? X's. Are there any X's that don't lie on the graph somewhere? Because if there are, then you're going to have to write an inequality to represent the domain. Can you find an X that's not on the graph somewhere? I mean, if I go on and on forever and ever over here, is an X going to always hit this blue graph? Sure. Now, because there's a jump here at -1, and I go this way, -1's a part of this graph, but not this one. If I go this way, is there anything that X won't hit this graph on? Well, if I move to the left for X, is there ever going to be an X that doesn't hit the red line? No, it's always going to hit the red line. So in this case, the domain is all real numbers. Okay? Are there any gaps or missing terms, missing values for the y? Are there missing values for the y that don't ever appear on the graph? Where? Yeah, right here. All these, there's no y values right in here. It's missing. Okay? So when I write my range, I have to exclude those values. Or we write inequalities for each piece. So what our range ends up looking like is an or statement. Because the range for this, right, all these values down here work. So at -3 for y, less than -3, all those values down there work because they match up to the line. Everything less than -3 matches up to this red line. Or everything greater than 2 matches up to this line. So that's where my inequality comes from. That's where my range comes from. And we write it as f of x because we actually aren't talking about y's here. I know we're writing y's and thinking of it as y, but it's really f of x. So when I write my range, I have to write it in terms of f of x. And so I get two parts. F of x is less than negative 3, because here's the negative 3. Can't be equal to because of the open circle. Everything below here is on the red graph. Or, because they can't be in both places at one time, it's greater than or equal to 2 because it goes above. And 2 is included in this answer for y. So my range is a little bit different now because of all of these excluded y values in there. Okay. Now, if there were gaps in the boundaries, you'd do the same kind of thing for the domain. So in here, since they kind of overlap, or they jump, there's no missing values for the domain, for the x. If the boundaries make us have gaps in between the pieces horizontally, then our domain will reflect that in the same way that we do in the range, okay? Good? All right, let's go the other way. So go ahead and take a picture of this screen. So here's the graph. Now we're going to write the equation. How many pieces?
3.
How many equations?
3.
How many sets of boundaries? 3, okay? So for each piece, for each equation, there's a different set of boundaries. Okay, and so we have to identify those first. Now, here's the way that I like to start, because I want to do the boundaries first. That's the easy part. Okay, because once you've knocked the boundaries out of the way, then you can just focus on writing a linear equation. Okay? So, here's how I like to start. On the left, it's f of x. Again, we're thinking of it as y. We're thinking of it as y. And we do a left brace. And now I'm going to leave some space here because over here is the conditions, the boundaries. If, then an inequality. If, then an inequality. If, then an inequality. And up here in yellow and red and black, I show where the boundaries have to be. See this piece? I have a boundary here with this open circle, and everything left will be the rule for this graph. This piece is a line segment. There's a left end and a right boundary. Left boundary, right boundary. So I'm going to have a compound inequality for my boundary here. And then this piece over here goes to the right, so I have a left boundary, and then it's going to the right or greater than. So let's look at each piece at a time and write each boundary one at a time. Okay? And we'll start with the yellow boundary. Okay? You didn't see that. What x value goes with this yellow line? 1. So the line, if I extended this yellow line, it would be x equals 1. Okay? It's an open circle, and it goes to the left. What would my inequality be for that line, for this boundary, for this piece? X less than 1. Okay? Oops. The first boundary. If x is less than 1, based off of that yellow line, because to the left of that line, 1 is the x value. It's an open circle. That's why it's not or equal to. Okay? Questions on that? All right, let's look at this next one. I have a left boundary and a right boundary. What's the left boundary?
1.
What's the right boundary? 2. How do I write that inequality? It is an and statement. It's just like an and statement, but we can write it as a compound statement. Okay, so x has to be bigger than 1 and at the same time less than 2. And because the dots are filled in, there's or equal to. So my secondary is going to look like that. If 1 is less than or equal to x, which is less than or equal to 2. Another way of saying that is that x is in between 1 and 2 inclusively. Inclusive meaning you fill the points in. Okay? So again, this just represents the boundaries. This is just the boundaries. What's the boundary going to be for this one? X greater than 2. How about or equal to? Am I going to have or equal to? Why not? Open circle. Okay. So now once I have all three of my boundaries, I can spend time focusing on the actual equations. Because once I have the equations for each piece, then I've written what the piecewise function is. Okay? So let's start with the first one. What do I need in order to write an equation? Y-intercept and slope. Okay? So on this first one, what's the y-intercept? 3. Right there, right? So I know that the y-intercept's right there, which means what do I know about my equation? What part do I know now? Y-intercept, so what does it look like for this one? Plus 3. I'm going to have a plus 3 in there, right? That's the y equals mx plus b. What's the slope? How do I figure it out? How do you figure out slope when you have a graph? Count. So how do I count? From there, so let's say I'm going to count from the y-intercept to the open circle. How far up do I go? 2 and right 1. So that's 2 over 1, which is 2. Okay? So 2 over 1 is my slope, which means my slope is 2. So how do I finish off this equation? 2x plus. Okay, that one's done. All right. Question. Just any 2 points. How do I know that this one goes with this? Because the only place on the graph where x is less than 1 is over here. Nope. Nope. This boundary goes with this one, this boundary goes with this one, and this boundary goes with this one. So we're going to write a rule for each one of those. Okay? All right. What's the y-intercept for the second piece? There is none. Okay, so where you just can't do it? Can we figure it out? Well, we can figure the slope out. So here's the thing. Okay, this one works out nice because it's easy to figure out, right? How do I figure out where the y-intercept is? You just kind of back the line up, right? Back the line up, I can see that it's going to hit right there at 2. This works out okay. So the equation still falls in line that way, even though 2 for the y is not a part of that graph. So if it doesn't line up nice like that, you have 2 points. You can find the slope. All you need is 2 points to write an equation of a line. You can find the slope, plug it in, solve, and find the y-intercept that way, like we did in 2-4. Okay? Now, this one works out nice, so my y-intercept is positive 2. What's my slope? -1. In my example, I went from here to here, so I went down 1, right 1. If you went from the bottom point to the upper point, you'd go left 1, up 1. Slope either way is still -1. So my equation here is going to be negative x plus 2.
Why is the 2 this one? I mean the x.
The y-intercept.
The y. It's the y.
Because if I continued this line, it would hit y at 2. Okay? All right, now the last one. What type of line is this? Horizontal. What is the equation of a horizontal line? What kind of form does it come in? Y equals some number without an x. And all you got to do is look at all the different points on here. What's true about all the different points on here? Y equals what? 3. Y always equals 3 on this line. So that's all I need to have for my equation. Okay? Y equals 3. Now, make sure when you do this, notice the only thing on the right side of this brace is the rest of the equation. So there should not be any equal signs in here. You shouldn't have any y's in here. You shouldn't have f of x written again. Okay? It's just the second part of the equation. This part in front takes care of that. So this is just what follows the equal sign. And my boundary's over here, and I'm good to go. Okay? So, not hard in terms of trying to write an equation for a line. It's complicated, though. Because there's so many different things going on at once, you have to separate them all out. Once you find these, I think it's easy to do this part. It's easier, okay? But like I said, it's complex. There's a lot going on there, okay? All right, next, step functions. Step functions literally look like stair steps, like floating stair steps. All you have is the horizontal part, the part you put your foot on. It's like there's no vertical parts to the stairs. It's just the steps themselves. And the most common one that we're going to look at, oh gosh, there's so many other things. They look like stair steps. They are also piecewise functions because they're not connected. And the most common one that we'll look at is called the greatest integer function. Notice this is not just a regular bracket. It's like a double bar bracket. I'm going to talk about what that is here in a second and let you catch up. The greatest integer function converts any value that's in here into an integer. And here's how it does it. It's the greatest integer less than or equal to that value. So it never makes the number bigger. It will only take the value in here and keep it the same or make it smaller. I understand that this is confusing, and 4th hour, I confuse the children. Okay? And I'm not going to do that this period. It will only take this number and make it smaller if it doesn't keep it the same. So like an absolute value that turns everything positive, this one will turn everything into an integer. But it'll never make it into a number bigger than the number that's already in there. It'll take it down to the next lowest number if it's not already an integer. And we're going to go through an example and you'll see what I mean. Okay. So the output value of the greatest integer function will always be an integer. It will never give us an output value that's a fraction. It will never give us an output value that's a decimal. And it will never give us an output value that's bigger than the number that's inside those little brackets. Okay? All right. Should we look at an example? Perfecto. Here we go. Here's an example. Graph the function, identify domain and range. So, h of x, remember, think of this like it's y. Y equals the greatest integer function of x minus 5. Now, in order to graph this, I'm going to use some points. I'm going to use a table of values, and I'm going to show you what I mean by it always giving an output value of an integer that's never bigger. Okay? Once you get the hang of how to do this, you're not going to have to plug a bunch of decimals in. But today I'm going to plug some decimals in to kind of give you the idea, the flavor for what's going to happen. So here's my table, my XY table. And I'm just going to plug those values in and we'll see what we get. What should I start with? 0. Okay, so I'm going to choose 0 for x. I'm going to plug it in. 0 minus 5 is what? Very good. Okay, now, negative 5 is an integer or is not an integer? It is. It is an integer. So, again, what the greatest integer function does is it turns everything into the integer. It'll never make it into a bigger integer. It'll make it equal to itself or the next smallest one down. Okay, since negative 5 is an integer, it just keeps it the same. The greatest integer function will turn negative 5 into negative 5 without the brackets. Okay? Correct. So if it's not an integer, and I'm about to show you an example of that. So if it's not an integer, it will take it down to the next smallest integer. So I'm going to choose 0.5 for my next one. Because I know that that's going to give me something that is not an integer, right? Because 0.5 minus 5 What's 0.5 minus 5? Negative 4.5. So what this will do, it's going to convert that into the next smallest integer. It will never make it bigger. So what is the closest smallest integer to negative 4.5? Negative 5. Negative 4 is bigger. Negative 4 is bigger. It can't ever make it bigger. It can make it smaller. And the next smallest integer is negative 5. Okay? Now, if I picked other decimals, right? If I had 0.2 in here, this would be negative 4.8. What would it convert it into? Negative 5. If I put 0.7 and I plugged it in here, and I had negative 4.3, what's it going to convert it to? Negative 5. When does it change to negative 4? What's the first value that will change it to negative 4? Okay. 1. So if I put 1 in, so I could try all the decimals in between 0 and 1. Okay, and all these things are going to give me negative 4 point something, which will take it back down to negative 5. But when I get to 1, this becomes the greatest integer function of negative 4. Well, what's true about negative 4? It's an integer. So therefore, that produces the same value. So what's happening here is in between 0, including 0, and 1, it keeps it the same negative 5. But as soon as I get to 1, it takes it to the next value. What's the next x value that will change it to negative 3? 2. So everything between 1 and 2 will revert back to negative 4. It will give you an output value because all these values will be negative 3.9, negative 3.8, negative 3.6. Well, the next smallest integer is negative 4. So we have a range of values for x that will give me an output of negative 5. A range of values for y that will give me a negative 3. What happens is at 0 it equals negative 5. At almost 1 it still equals negative 5. And when it converts to 1 it jumps to negative 4. So what I'm up with is a range of values. Because at 0 it still produces negative 5. And it's equal to 0. But right when it runs up to 1, like if this was 0.9999999, and this was negative 4.000000001, it still jumps back down to negative 5. But as soon as it hits the 1 threshold, it changes to negative 4. So what's this compound inequality going to be for negative 4? What's going to go here? 1, and then this all looks the same, and then this is a 2. Okay? And so the thing with the greatest integer function is once you find a couple of those ranges, a couple of those inequalities, the pattern just continues. You don't have to keep doing it. Okay? What you want to be able to do is find the x value that will make it jump to the next integer. Now, because of the negative factors, it drops back down. If these were positives, you just drop the decimal and it's the same number. Okay? Because if it was positive 7.9, the next smallest integer is 7. Drop the 0.9. But for negatives, it goes the other direction. Okay? Now, let's talk about how to graph this. Because essentially what this is a piecewise function. I'm saying this is the boundary, and y equals negative 5 for this boundary. I'm saying y equals negative 4 for this boundary. Okay? It's going to look something like this. So for the first one, for negative 5, I go down here to where y is negative 5. So again, the direction of the steps, the open or closed circle can change. The slope of the steps can change. Don't give me one step on either side. Give me a few on either side. The spacing between the steps can change. The width of that step can change depending on the equation. But what I want you to do when you do your table is make as many values, put as many values in there as you can to feel comfortable with the boundaries and how many steps there are. Tanara.
This is super relative. What would you use this for in everyday life? Not everyday life, but in.
Probably nothing. Yes.
I mean, so if each one moved over like 2, you're saying that everyone would move over 2?
Yep.
And not one of them would be.
Nope. It's always going to be uniform. It's the slope. So think of this. Think about it this way. This is why it's called a step. A stair step, floating stairs. I mean, think about normal stairs that you walk on. You don't have like, one super long step and then one you got to take a giant leap to get to the next one. It's the same idea, right? I mean, I get it. Sometimes there's landings and that kind of thing, but most of the time they're all, uniform. Don't count the ones at the main building either. Those aren't uniform at all. Okay, but normal sets of stairs engineered to code are the same width and the same height from step to step.
Which steps are
Wait, the
uniform?
stairs in the main building
Yes.
aren't code?
No. If you see the first step's this big, and then there's a normal step. Yeah, no, it looks like it's sunk or something. I don't know. All right. Next, we got to get there. Oh, we still have to write domain and range. I didn't even do domain and range yet. We didn't do domain and range. Are there any x's missing? Any x's not on this if it went on and on forever and ever? No, there's not. Okay. Are there any y's missing? Yeah, there's a whole bunch of y's missing.
The only thing I haven't hit is only.
How about everything in between each step? There's nothing in between the steps. There's no y's in between those steps at all. No y's in between the steps. Well, guess what? The greatest integer function generates what? What are their output values? Integers. So our range for this problem is all integers. Z is the symbol for all integers. Yes, chapter 1. Z. Now, if all real Zookins, there you go. Sure. It's all integers. Now, depending on what's being done, sometimes you can add or subtract to the greatest integer function outside of the greatest integer function, and it won't necessarily be all integers for the range, but just watch out for that. All right. Last one, the absolute value function. Last one is the easiest one. I saved the easiest for last. What, does anybody remember what the shape of an absolute value function is? Really? No, that's parabola.
And that's used in.
No. The shape of the graph. Shape of the graph.
Is it a line?
No.
It's a big V.
It is a big V.
Well,
Is it like a
just said that, didn't I?
No, you said positive. Absolute value graphs are shaped like V's. Okay? They are always shaped like V's. So one of the things that will happen when you're making a table for your absolute value graph is you might pick values that make your graph seem like it's a straight line, that it hasn't made the turn yet to go up the other direction or down the other direction. And so I'm going to show you what I mean by that. Because we're going to start off the same way, and we're going to start with a table of values. Okay? And I'm going to start these 4 values, 0, 1, 2, 3. I want you to find the y's and graph them. Plug them in and graph them. Go. What's the first value? 0, comma, negative 4. What's the second? 1, comma, negative 2. What's the third one? 0. What's the fourth one? Positive 2. Here's what you should have got. And notice I put my points there. Right? It looks like a straight line. So if I keep going on the positive values for x, I'm gonna keep thinking that it's a straight line. So there's a point where you sort of have to abort. That's why I want you to plot the points as you go. Because at some point you're like, all right, this is an absolute value function. I know it's supposed to look like a v, so I need to start going the other side for x's. Okay? And as soon as you find it change direction, that's all you need to do is 1 point. I'll show you what I mean. okay? Because the absolute value function is a mirror image split down the middle, just like a parabola. So I'm going to go ahead and go over to the other side and check where x equals -1. So go ahead and do that and find out the y value. What's the value? When x is -1, what is y? Negative what?
-1.
It is -2.
Absolute value.
Absolute value of -2 is 2. Absolute value of -2 is 2. 2 minus 4 is -2. So, notice on my graph, okay, I put that point. So it made the turn. Okay? Please do not plug in -2 and -3. Reflect them. So I know that this point here is 2 away from the y-axis, which means I'm going to have another point 2 away on the y-axis. I know that this point is 3 away from the y-axis, then I know I'm going to have another point over here 3 away. Don't put those in. Just plot them, reflect them. Okay? And then you can make your absolute value graph. Okay? 2 more things we have to do. Right?
Boundaries.
We have to do the domain and range. Are there any x values not on the graph?
No.
If I move to the right, will it always hit to the graph? Well, if I move to the left, will it always hit the graph? Yes, so the domain is all real numbers for the domain. Okay, for the range, does it always hit all the y's?
No.
Where is there a boundary?
-4.
-4. So down here, -4, I have a boundary. It never drops below that line. So my range is going to be what?
Greater than -4.
Greater than?
Equal to.
Greater than or equal to. Now, again, my function is not written with a y. It's written with an f of x. So when I write my range, it should say f of x greater than or equal to 4, because -4, excuse me, -4 is on the graph. Okay, greater than or equal to -4. There's my domain. There's my range. That's the absolute value function. There's a lot in there. A lot in there. And I did a lot of talking today. I'm going to take this video and I'm going to upload it so when you're working on your assignment and you forget what to do, that you go back and watch that section, because there's a lot going on in here.